Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and this is the next installment of the Selfish Circuits and Loving Paths series. So I've returned after, what has it been, a year or so? I'm going to be including in this video an almost 2-year-old video that I took in Ohio. Later on you'll see that, but I wanted to show it, this process that I want to talk about today, both with the big motor and the little motor. So the next part of this video will be the big motor, and in this video what we're going to do is show how we can incorporate, not just with expanding the amount of batteries that we're using, but also with the coils now. So some of you have been aware of this who have come to my conventions, and this is something we've talked about and shown a little bit at the meetings. And the good news is we can do this without the trigger coil. So we've got a mess of wires, of course, here. So what do we have here? Essentially, we're going to run this a little bit later. Again, I'm letting the battery stabilize a little bit because it was just running for a couple of minutes here while I was getting it set up. So what I have here is the 4-pole kit here with the MOSFET with the gate driver. This doesn't have the Arduino kit, which I'll talk about in a minute, on it right now. But it does have so it doesn't have any of the speed control on it right now because that's not what I'm wanting to show. But what we do have is we're going to be running off of just one coil. And then, so the circuitry only applies to the one coil. And then we are going to, so let me just make that clear. You have the primary battery bank, which is 24 volts here, going into 12 volts. Now we don't have matched up batteries here or anything, but we're running the motor coil and the circuit through the two positives. So the 12 volt negative and the 12 volt negative of the 24 volt negatives are connected, and the 12 volt positives we're running the motor between. So that is what we call the Selfish Circuits Loving Path switch, I guess we could call it, number 2, where we're running, splitting the positives, right? And then the third stage process, which we call the third switch, is where we're running a box, right, between the output terminal and the charging battery. So in this case, if you haven't already guessed it, some of you did, we are, well, actually nobody guessed this part. I ran a motor coil in series with the output going to the charging battery. So in that case we have a charging battery here, which we're going to show running normally. And then the motor coil is going to have its own load. So we're still going to charge this battery, and we're going to run the load, which in this case is 10 watt LED. And then we've got 2 more coils. So I'm going to run in this demonstration just 1 more coil. I'll leave the 4th one off. And where would I put the 3rd coil? Again, it's not being switched by the circuitry directly. It's only in the path. So if I have the motor coil between the 2 positives, why not put a motor coil between the 2 negatives? And we're going to look at that first. So now, if we do that, and we are charging this battery off of that motor coil, I've got a high-speed diode here, and you'll see how effective it is. Then I could use the 4th coil across that path in the same way we did on the positive side. Now we can do it on the negative side and run a load off of that, which we'll see in the next video, or at least in the second part of this video when we did that with the big motor. So that's what we're going to do today. That's the major revelation here. This is a really, really big, important point, because it's going to say a lot. A lot about the potential of this motor kit, for one, because you're going to see that it cuts the efficiency right in half, or it increases the efficiency, doubles the efficiency, it cuts the amperage in half as we add the coil on the negative side. So then, let me just say here that the way I'm running this with the extra coils is not ideal. In other words, I'm just using the rods and the coils as I have them here. Now, if we go into different core material and we get into finely tuning the whole thing, then we can do a lot more. But this is the basic idea I want to show. And I'm not running the generator coils here because this is not my purpose. I'm not here to show the whole system running to confuse everybody with all the different things. I'm not shorting out the coils. The coils are just not being used at all. So of course, if I short out the coils, then the motor will be even more efficient, as we've seen in so many other videos. And of course, I could adjust with the Arduino board the speed control, and we can do a lot with this, is what we're going to be doing. Like I said in my last video, we're going to incorporate a random frequency into this so that this doesn't put out a constant repetitive frequency, which is actually dangerous for the body. It's not healthy for you. No frequency, well, very few frequencies are really healthy for the body on a repetitious cycle. So that's very important to me that we break this up, and studies have shown that, and I've shown that in the patents, that if you break up the cycle, at the cellular level, your body isn't manipulated by this frequency. So we'll be adding that, which won't affect the motor's performance. And we would like to do that on a global level, bring this wisdom to the world to help people prevent cancer and so forth. So, a couple of things then. The reason why these are sticking out, because this will be a double stacked unit, and I wasn't going to bring that in there for this demonstration to cause too much variables. Now, here's a very, very important point, that the way the kit is right now, we are running the primary battery is driving the gate driver. Now we can only do this if we don't do anything extra special on this kit, because the gate driver is very, very sensitive. And when I actually tried to run it that way, doing these extra processes, because they are special processes, I blew it out instantly. And so I have to use a separate battery like we do on the big motor kits. This is very important. I was trying to overcome that, which I couldn't do, because when there is pulsing on the line going to the charging battery, it also affects the primary battery, which I've been saying for years. The primary battery is receiving some charge back. That's why a lithium battery and a supercap will actually be able to receive more of the charge back than a lead acid battery, which only wants to go in one direction. But the lead acid battery can self-charge in that way too. But the bad news is, when we go with the gate driver, which is very sensitive, which makes a great improvement on the switching, it is very sensitive. Now you can add some capacitors there and resistors, and this is what we were trying to do, but I'm not comfortable with it when it's so easy just to isolate it. Now we share the ground terminal with the primary negative terminal, which is in this case on the charging positive, a battery bank number 2. Like I said, normally this is, these are, all 4 batteries here are equal, and this is going to be 2 12-volt batteries in parallel, while this is 2 in series. But anyway, we're going to go to the primary, or the charging negative. This is the primary negative, sorry. Charging positive. Well, it's kind of confusing until we look at the diagram to explain which terminal I'm talking about. But anyway, the negatives are tied together. Normally, we make this kit where the positive terminal of the gate driver and the motor terminal positive are the same. And we can get away with that on this, provided we don't do any third stage process, is what we're doing today. And so yeah, it blew it out. When I work with the bigger motor, even without adding any extra processes, there's so much negative energy produced, there's so much noise on the line, that it blows it out no matter what I do. And that's why I've been a little delayed in getting my next video for the big motor done, because I was trying to overcome that without going to the secondary battery. Now, the good news is it doesn't draw very much energy at all to run the gate. They're very efficient, and in this case we're powering the Hall, an opto, and the gate. Now with the Arduino, we don't need the extra opto in there because we programmed it into it, reverse it. So all we have is the Hall and the gate driver and the gate itself. So that is something that could be easily powered with the generator coil or whatever, kept, we're talking about very low milliamps. So what else to say here before we start this up? We can run various loads. I'm just showing 2 different loads here. A bulb and a battery. And I guess guess that's it for now. Let's restart our meters so they don't time out on us. And then we'll go with this clamp ammeter. I want to make sure that's all easily viewable. Yeah. Let's do it like that. Hopefully I can see that. Not too much glare from the light. All right, so in this case, it's not going to be self-starting. Now, of course, we can do this at a higher voltage and all that will self-start. And I haven't glued down this hull yet because I'm going to be making it double stacked and all that. So I'm going to give it a little spin, just a little start, and we can watch the ammeter. Now I'm running it normally to start, so we want to compare the difference. We want to get it up to RPM, and then we want to switch over. So let's just go like that. And so you can see it's going to draw 800, about an amp at first. And now, of course, this is going to be only 1,000 RPM. And then because we're only running one coil at first. So you could do this, you could run 2 of the coils in parallel. And just do this with process what I'm going to do today with the 2 extra, or you could try and run all 4 or all 3 coils as slave coils. So actually what I want to do is switch this meter down a notch to the 2 amp setting so you can see more readily the change. So we're at 429 milliamps, 28, coming up to RPM, and I'm going to look at the so 1095 RPM. You can see the meter. All right, so 427 milliamps. Now we're going to run the one coil, let's call it coil number 2, in series between the 2 negatives. So I've got these 2 wires here. So the green wire comes over to this green wire, and then the yellow wire is the bypass, and then the other end is this red wire. Sorry, I don't have perfect color coordination here. So now we've disconnected that, and what happened to the amp drop? It immediately cut in half. 230 milliamps, rising slightly. But now we have a load. Actually, I have 2 diodes here, which I really don't need 2, but I have that because I had a battery on there. And now this battery is not being charged yet. So I could put it on the other. Anyway, this is not trying to prove a lot of things here. This is just trying to show you how to do it. But I want to look at a couple numbers here. So now the RPM on this case, the RPM goes down a little bit. But for the sake of, so we've got 1029 RPM. Oh no, yeah, but around 1030 or so. So we dropped the RPM a little bit, but we cut the amp draw almost in half. That's a pretty good result. Now, we can look at a couple of the voltages while we do that. So this one, of course, isn't being used yet. This one is going to be the next one that we do. So let's go over here. First of all, so this is 1259, 1260. So this is charging like normal. And of course it's going to charge more when we apply more current through the system, like I just showed there. And then of course this also will be affected in the same way, the charging battery. So 1067, 1083, it's going to be charging twice as fast. So far the only benefit is we're pretty much cutting the motor power amp draw almost in half. Now, let's go up to the next level. So let's look at, so the charging battery right now is 1067, right? And now we're going to go, oh wait, we want to look at this battery. So this battery is the one that is going to be charging so like I said, 1227, it's still coming back down from when it was being charged. Now watch what happens. The amp draw should still stay the same in this case. Now this is on going to the output. This is where we have the stage 3 process. So the amp draw remained the same, but look at the charging rate of this battery, 1340, and climbing fast. Now this has been a negatively charged battery. So the amp draw remained the same. The RPM remained the same. The RPM is about 1020s. Like it just was. It hasn't changed. Now, if we look at $10.61, $10.63. So this battery slows down charging, and the other one charges up significantly faster. So this one is stop charging because I don't have it on. Or no, that's not stop charging. So let's turn this one off again. Let's go back while under voltage, while we're checking the voltage. So you can see that's coming back down now, under rest, 1265. So it really did push the battery a good bit. So now if we go back to disconnect, or bypassing the second coil, we're back at square one. And we have the higher amp draw, and that's all the same. So I'm just wondering if I could do something here, because I don't have any jumper clips on me immediately here. See if we can speed this thing up a little bit. Just maybe play around with these things is the dangerous thing to do while things are running. Alright, there we go. Now we just added a second wire. And now let's try all this again. Let's let it stabilize. So now we've got all 4 coils running. Maybe give us a better example. I could get some good RPM readings here. Oh. It fell off. There we go. So now, of course, if you remember the second stage process, the operating voltage is between the 2 batteries, the 24 volt bank and the 12 volt bank, which is, in this case, between the 2 positives. We have only 10, we're only running at 10.66 volts. That's what you got to remember. We can look between the 2 negatives as well, but right now they're the same because there's nothing in between it right now. Okay, so we have only 10 volts because this battery's become charged, which, because it's very small, 1270, and this one's at 23, hasn't really changed. Oops. So yeah, 1063, and we're at, oh, this thing keeps falling out. It's not really accomplishing, this video isn't accomplishing what I want. So yeah, we're at 600 milliamps going down as it's getting up to speed. Hopefully that doesn't slip out on us again. And if you want to look at this battery, 1210 on that one. So now, of course, the beginning battery is going down with a 537, 36, still getting up to speed. (2,000 RPM). Again, it's only at 10 volts, and it's only 2 of the coils right now that are running. So we're at just about 500 milliamps, 516, 15, 14. Still getting up to speed. (2000). 2006 RPM, 510 milliamps. So let's just call it at that, and then we will look at what happens when I disconnect this. Oops. 183 milliamps. Alright, so we don't have anything, we don't have that third battery hooked up yet, fourth battery. So this one's 1266, the running voltage again. (1032). RPM, I notice, has gone down quite a bit. It's at 1554. So anyway, that went down, but obviously we're at 230 milliamps. So it initially dropped really low because it was piggybacking off of the built-up RPM and the momentum of the flywheel. So this one isn't quite the same as what I was doing with the big motor, which actually RPM was going up under this circumstance. But the intra is cut in half here. So let's see. So let's do the other one now. Let's go back to this battery. Of course, this thing turns itself off. So 138 milliamps. 138 milliamps. And now we're going to disconnect. So this is 1241 again, and now it will go up pretty fast. And then we're back to where we were before. Now, of course, we've got 2 coils to 1 in that scenario. So there's an imbalance in that sense because I've paralleled 2 of the coils. Anyway, let's just turn the switch off for now. And then let it slow down and stop. You can see there's some residual, the meter is showing actually 19 milliamps more than 0, which is the way the meter works. It always has to be zeroed out to get it changes a little bit in that sense. But so anyway, here's the voltages. This voltage, obviously this one received a good bit of charge. The primary battery is now at rest. We'll look at this battery voltage, 1250, has received charge. So anyway, pretty much all the energy has flowed from the one battery bank supposedly to this battery bank, and in a loving path. And so otherwise it's not just shorting the energy across itself like it normally would with this circuit. It's going from this battery supposedly into this battery and then returned back. And so, and this third battery bank has also received charge like we normally get. So this one charges at the rate that this one discharges. And also this one charges almost at the rate that this charges. Now when we do these extra processes, this battery can receive more charge. Not really with these motor coils with their iron cord. We have to do some different things. And that's not the object of this video. But if you look at the Benitez system with the higher frequency and so forth, we can rotate these battery banks around indefinitely and actually have a surplus of charge while we're running our loads. In this case, we have a motor running for free, which we haven't even shown the generator coils. So if we do some extra processes, then we can actually see all the batteries charge, as I've been saying all along. And I've been giving, different pieces of information for those who have been watching. So again, let's look at these voltages. 1245, the difference between them at rest is 1123, but under load it was, when this battery had a higher charge and this one a lower on the draw, it was about 10.3 or 2 last we checked. And so it was only operating at 10 volts. So again, this is just showing you more of the loving path benefits. In other words, we have the energy running through the, let me just leave this on here. We have the energy running through the path. And if we have the right kind of path, then we share the load. We share the energy, so to speak, rather than just, you think of a voltage drop across a resistance. So in this case, if we check the voltages, which is what I've shown in the other video, you'll see the second part of this video, you can see the voltage drop over the coils that are running. And it's very low. And depending again what kind of core material we use and what so forth, other processes, we could actually make that 0. When we have the coil as a tank circuit, is you have to look at all this as various tank circuits in which they are in resonance. When they are in resonance, then you can add as many of them in series as you want, and then you can perpetuate the output. Now we're not running these in resonance, and so this is just a very basic demonstration of what you can do with a gain. I'm showing a gain here by these processes, and in this case we're running the motor with less energy, considerably less energy, and we're getting more energy out. We're multiplying it out. So let's see what else. There's many things. This will open up a whole bunch of doors, I suppose, for everybody when they look at this and understand the implications. So I've said this about a year ago that there was more involved, and this is just another point to make in this video, in this series, I should say. And so really what's left to be done is ideal, what's the term? What I call the third stage process, or the box, is what we're showing here today. Now, it wasn't exactly, one of these coils by any means, but you can see what adding a coil in series does to the system. Now, like I said, once we added that process, then there was more energy on the input. Now, I didn't show the oscilloscope. I do that in the next part of the video, you'll see. But when you add each one of these processes, like I'm showing here, then you're going to have more energy on the input side. And that's why it blows out that gate driver. It's too much for it. This is where we have more energy coming back to the primary batteries. And I'm not sure what we started off with. I'll have to look back on the video here. But we can actually send more energy back into the input and keep it all charged. And not have to rotate batteries around. In fact, we just have all the batteries charging in that case. So with the right core material, with the right kind of third stage process, then we can produce either the 0 voltage, the 0 point, whatever you want to call it, process where it's actually all at 0, which like Gabriel Cron called, in his network system. Or we could cause the battery to discharge or charge. Remain the same, charge or discharge. And in this case, I'm just showing it done with the motor itself. And this is just a very basic demonstration. I'll probably show later on it all beefed up and really flowing. But this is what I just wanted to show, the basics. I finally found the old video that I took in Ohio. You can see the video coming up now. The second part of this video is in, I think it was September, was it either September or October of 2015. It's almost 2 years ago. And I put it somewhere, and I just found it right now. So I thought, okay, I'll publish that. And the reason why I didn't show it initially is because I made a mistake or two in the video in which I blew out a transistor, and I wasn't really too inclined to show that. But there's three engineers in the video, and the one who's asking the questions is the mechanical engineer, so he's not electrical engineer. But the two others are electrical engineers, and so you can hear their comments in the video. So that video was, exploring this process with the coils, like I'm showing here, but with the bigger motor. And there you'll see the RPMs more affected. And so again, it depends on the particular, there's several factors that affect all of this with the RPM and everything. There's still sweet spots and what have you. But I wanted to show this on both motors running and give you an idea of what you can do with this. So, what else is there to say about that video? I'm not going to show the whole video because I go over, in the beginning of the video, a whole bunch of explanation. And it's more of a private thing. But I will show the demonstration of the motor. And in that. So this, again, like I said, opens up a lot of doors. So you can see his batteries come back down. And then this battery right here, 1051. That one is quite discharged. It's negatively charged. That's why. So, like I said, what you can do with this process is make a motor like this. You could make it run your loads and be a prime mover. And this is not, I actually don't even want to go this route. In the future I'll show that we'll just be concerned with the generator coils. The motor will run itself through this process one way or another, several different options. And then the generator coil output will be multiplied indefinitely, as much as you want. Again, if you want to understand what I'm doing with this whole Loving Path series, you want to go back to earlier videos that I did and go back to the Tesla one-wire lectures and read carefully, see what he's demonstrating there, and that's what we're doing on a very low voltage, low frequency level here. And of course the Benita system as well more clearly shows the whole process with batteries. And but they're very similar. And then of course the Daniel McFarland patent, which predates both of them. So there's a lot of people that contributed to this understanding over the years, and I wasn't aware of all of these things till at the beginning of my research, of course. I just assumed it came from somebody who will remain nameless in this video. But he actually didn't invent anything, as far as I am aware. But anyway, the process, when you think about it, go back to that Tesla one wire. When you have a high frequency, high voltage pulsing across one wire, like he shows in that video, then you can actually tap between any 2 points along that line, even very close to each other. The higher the frequency, the closer you can get and get real power. But you have to understand how to tap that power. And in this case, because we have very low frequency comparatively and low voltage, we run through the coil. But anyway, you can actually, if the coil in this case, you can have other things beyond coils too. But if those two nodes and the circuit between them or parallel to the one wire, so the two nodes are the points where you're tapping into the one wire. If you have that in resonance, then it will not affect the line at all. In fact, it can contribute to the line like we're showing here. At least in former videos I showed more better example than using coils here. I'm just using coils to show you and reveal this finally and showing you what you can do with the motor itself. Now, if you run them in resonance, you can tap as many taps as you want across this whole one wire system. Now notice in his diagram he has a P plate at the end of the one wire. And it's kind of suspended in air. It's not grounded, but it's like an air ground. So he's running to a destination point. Again, the destination point isn't the loads. The loads are in series, but they're not really in series in that case. They're in a parallel configuration in series with the wire. Well, in parallel with the wire in series down the line. And then he has individual P plates in various configurations. So when you understand that and you apply all these principles I've been talking about, then you can actually multiply out this energy as much as you want. One of the reasons why I haven't really gotten into this, because I want to protect people from the dangerous frequencies that are not healthy for you. And so the really high outputs are very bad for you, and they're very dangerous. So I'm not going to be showing that until we fully develop. One of the things, though, that I did come up with was that breaking up the frequency so that it's not always the same. And so that's very important. And then there's two types of shielding. I was going to show a video, but it's not fully done yet, where I have a shielding for the system as well. And then not just the zinc, but a sort of an antenna of sorts, Faraday cage, that's not just a shield, but it's an absorber of the energy as well. So when you pulse the coils, they're like little EMPs, right? So we have to protect against that, our electronics and so forth. And then of course biologically we don't want to receive repetitive pulsing, especially like the 60 hertz, 50 hertz signals that we're getting bombarded with all day long. So anyway, like I said, with the one wire system, if you think of our output as the one wire, after the diode going to P, which would be your battery plate, that's the way you got to visualize this. So then, like I said, if you really, like we've been going, I think, 12,000 RPM with this motor. 77 volts we went with this driver circuit, but we had to isolate it like this, the driver from the main battery. So when you get to really high frequencies, which that still isn't very high, it's high for this motor of course, but when we go with the high frequencies, which we can do now with the speed control and the Arduino, we can create the frequency within the frequency, and then, like I said, have another frequency within all that to disrupt it. As long as you do it every 1/10 of a second to 1 second, then you create a better biological environment. But anyway, we can create a very high frequency. We can pulse this really fast within the on time and create that benefit. And we have seen the gains with that, where with every pulse there is still an output. The phenomena that we're desiring in the battery charging or powering the lights or whatever is there with each pulse, on, turn on and off. So the gate drivers now that exist, we can actually accomplish what you can with a basic spark gap. Now there is still more benefits with the right kind of spark gap. It's actually no spark at all is what you want. There's more benefits still with that than what we can accomplish with semiconductors as they presently are. But with your basic spark gap, this now can accomplish the same thing. So I'm impressed with the gate driver. It's made a huge improvement to these kits, and now it takes you above the 1-to-1 charging rate, and it allows for these kinds of processes now without the trigger coil. So in this next part of this video, you'll see me running it with the trigger coil. And of course, because of that, the trigger coil gives you limitations, like the sweet spot changes pretty noticeably. You'll see at one point in the video where the amperage draw is going down, and then all of a sudden it goes back up because it hit that spot, right? You know, it's like shifting gears. So you don't see that with this setup because it maintains that sweet spot. But there still are sweet spots in when you add these more complicated processes here, because you're having to relate everything. This is what I've been trying to say. You have various impedances. You have your loads, and you have your coils, the core material that you use, and of course the timing of the motor, and the on time of the motor, and so forth, the impedances of the batteries, of course. So all of these relate to each other, and now that we've got with the computer control, we can actually monitor things carefully. Like I said, if we want to keep this isolated on this battery rather than on the line itself, Otherwise it will be ruined, or negatively affect the process. But we want to monitor things and adjust things and make it more regulated. But I think this is definitely beyond what's even needed for anybody, what I'm showing here. This is the next level up. And it really is the end. When I said this is the last thing I'm going to show in free energy, which somebody quoted that a year and a half ago that I said that, it really is, because there really isn't anything that I care to get into beyond this, because it's unlimited energy and it's not exotic parts. Now if we get into the ideal resonant circuit in the black box, where it's really at 0 voltage, in other words, the load isn't there, according to the source, it's its own energy source, then we can get into more exotic parts there. Very fast switching and so forth. So again, what we've done is let's recap from the start. We started with the basic circuit where we ran, we took a fan, for example, just a motor, DC motor that runs a load and discharges its own battery because it's a closed loop. There's a flyback diode on there that was also a closed loop across the coil. And that added a little bit more efficiency in your regular conventional motor, but essentially was not recognizing the potential of the negative energy that was being produced. It was a negative force, destructive force, which they had to protect, just like you have across the MOSFET flyback diode there as well. So now we then charged the second battery instead of letting the flyback diode go across itself. That was stage 1. So this is, I've been showing this now for 13 years. Let's see, yeah, about 13 years or whatever it's been. And others before me, but Benitez was doing this 100 years ago. And same with 140 years ago, McFarlane. So then from there, I showed, well, we can open up the circuit to charge another battery. So across the coil, we create a tank circuit. Instead of going across itself and being useless, or adding a little bit more efficiency to the motor, we gate that out through that diode now to charge a battery. So that was stage 1. So stage 2 is doing the same thing, but with a battery, another battery. So we went from 24 volts to 12 volts, or 36 volts to 12 volts, or 48 volts to 24 volts, or whatever, just like Benitez showed 100 years ago. So that was what I was calling the second stage process, where you are running another load in series with the return loop coming back to the primary. So most people didn't think of that because in their minds energy is dissipated across resistance, and they don't think of terms that the battery is discharging itself. The primary battery is discharging itself across a load. The load actually isn't diminishing the battery. What's diminishing the battery is the loop back to itself. And at the rate of the load, and it seems like a play on words, but it's not. because we showed that with the capacitor, whether you have a load or not, the same amount of energy ends up from one capacitor to the next, with or without the load. So it's not the load only regulates how fast the battery discharges itself. So it's very important to look at that the right way, because otherwise you dismiss that fact that the battery is discharging itself. So if you manipulate the battery to power a load and not actually return, and have a real open loop, like a one-wire system, then the battery will never discharge. So that's more or less what we're doing when we have the right way of keeping the battery from discharging itself. Now I want to make that distinction here because people want to always back pop the battery, like the Bedini Tesla switch, which wasn't a Tesla switch at all, but it was a Bedini switch, Brandt switch, or whatever, whoever came up with it, the Watson machine, all those were back popping the primary battery, the source battery, which is destructive to a battery, to go back and forth, right? You don't want to do that. Instead, you want to actually create what I'm talking about is a true open loop, or create various processes like the Bill Fogel process in his patent, the charge barrier, where, again, it's a very similar process where you have a resistance and a capacitance in parallel, and they create a very high spin pulsing in themselves, which actually can block the charge from going back to the primary battery. So there's various ways to do it, and then of course when we get into the Tesla one wire, we've got no return, right? So this is all kind of, what I've been talking about is all kind of a combination of those kinds of ideas. And then of course, the idea of the tank circuit is also a floating ground. So it's not connected to the ground of the charging battery. In this case, is in a floating ground position where it's not connected directly to the return ground of the primary battery. So this is very important as the stage 1 and stage 2 process, because now we've created a whole lot more potential energy usage with the 2 battery banks. Well, it's adding the second battery bank instead of just the 3. So this is, again, stage 2 that I'm still talking about. But when we go into stage 3, now we're adding additional branches off our tank circuit. So we've got one tank circuit, and now we've put another coil, in this case, for this battery, we have another circuit across that output. And then this then becomes another force that sends power back to the primary battery and the motor. So the motor can speed up when it's ideal. And there's more energy everywhere. But it has to be all phased carefully. Like this isn't phased, you've got wires running here and there, and each one of these wires has resistance in them. So this is not set up ideally at all. You want short wires, you want to do things very carefully. You even have to have some shielding in certain cases and what have you. There's a lot to know about this. I'm just showing the very basics. But the idea is sharing the load. That's why I'm calling it loving path. It's a path that shares, and it's giving, loving, giving path. So the more that we do that with the right kind of receiver, so this is the next spiritual point to this. If you have something that doesn't want to receive it, I just came up with this right now. So if you have a bad person who can't receive the love that you give them, then they trample it underfoot. Don't give your pearls to the swines, right? As Jesus said. So you have the right kind of tank circuit, which is in resonance. It's so appreciating the gift that it's given that it's just filled with warm vibrations. And so what happens is it has received this energy sufficiently, and it has multiplied it out again, passed it on to another, which hasn't diminished the source of the gift. And that's the way you got to look at this whole thing, that as many receivers along the line in different parts of the circuit, the whole system as I'm showing here, can benefit the whole. As long as it's all in harmony, you know, you have resonance here, resonance there, in harmony with each other. And sometimes that can be so much that it overwhelms and self-destructs. So there has to be a proper harmony, a tempered harmony. Too much of a good thing can be not a good thing. So that's what I'm saying, is you can multiply this out again and again. And one reason why I didn't show this, and I've let this span out for so long, was for many reasons, but one of them is I didn't want a flood of phone calls. Rick, how do I get that? Every person that I've shared this to, well, most people that I shared it to were bugging me with all these questions. I don't have the time for it, so. But I wanted to see too what people would do with what I shared earlier. And, you know, frankly, people haven't really cared for the most part. So I didn't really care to put too much into it, because most people, there's only a few people really that cared about this. So, and that's the way I'm looking at it, that I'm not going to bother too much with it, with people on YouTube, because there isn't really a whole lot of appreciation. So, but anyway, I wanted to share this right now, because I just feel it's the time to do it. We may be facing some hard times coming up, with some world wars, it looks like, are in the mix here, and feels like kind of like the quiet before the storm. You know, I kind of see that Trump is kind of like a repeat of Bush on steroids. So we're coming up to that time period in Bush's administration where he brought on 9/11. So who knows what's coming soon. So I felt like I should share some of this stuff while I can. And but really, this is everything that you need to know. It doesn't have to be done with the motor. It can be done various ways, different kinds of motor configurations and so forth. But this is the whole idea of how the energy works. Now, I'm not explaining it in perfect terminology, but it should be something that the average person could play around with and perfect, at least to a level that they can have all of their power needs met. So for me, what's important for me now to do is to develop these things out in actual products that people want. So for example, do the things that are like the conventional aspects of things, like the programming we're working on, and the automated systems where you switch the batteries around, and then of course the various sizes of the motors. And then from there, I think we're going to do fairly soon a heating system, both with a motor and without the motor, where we create heat using batteries. And we can get into a batteryless system. It's a little bit more involved to do. And the really high output systems require a lot of engineering and more specialized materials. But when I say high output, for very little input, high output. And but with multiplying this out is what this video has been about. So multiplying it out is really it's just an extension of the third stage process. It's really maybe the fourth stage, and this is what I'm showing here in this video is more like a fourth stage, where we're applying the principles of the third stage to in the sense of multiplying it out. Now I'm not showing that ideally. There's a limitation with the parts I said we're using here, but you get the idea. And with faster switching materials and correct phasing and bringing the components into resonance, that's when we can multiply it out. So really after that, there's nothing really more to be concerned with. You know, so now on a quick note, I wanted to do a whole video on this, but some of my batteries have off-gassed, and so I popped open the lids here on these gel cells, and you can put a little bit of moisture, water back into them. It's kind of a tricky process, but some of you may have experienced that over time and not realized why your batteries stopped working or became less capacity. It's because they've off-gassed and they've let off the gas, and so they cannot have any capacity while they're dried out. But it's not like a sealed lead-acid batteries. AGM batteries are easily damaged. They're not ideal. I don't recommend them, even though I have a whole bunch of them here. It's better to have just sealed lead-acid batteries than the AGM batteries. Well, like this one's a sealed lead-acid, and but this one's a sealed AGM. So there's a difference there. Anyway, I think I'll do one more voltage readout of these batteries. This one, you can see it didn't draw anything off of that battery because it was only driving the gate driver. So 1213, this battery has settled at a much higher voltage than when we started. It was in the 10s. This battery, 1234, and then of course this one you can see 23. Oops. 2356. I just moved the water around there, so I have to dump some of that water out. That was a battery that was at like 0 volts because it was damaged. And then I added the water in it, and now it's working again. Oops. So 1047, So this one has gone way back down. It was at like 10 volts or something when I started. So there you have it. Let's watch the second part of this video, and I hope you enjoy it. I think this is the most comprehensive video that I've done. It's really a summary of everything. So I hope you enjoy it. Thanks for watching. Okay, so here's the system. You guys can come up in a minute, but I just want to show a couple of things here. So this represents battery bank A, or 1, I should say. 24 volts here. And then this represents over, let's see, which one is it?
Front one.
This one right here is battery bank number 3, the charging. So this is normally the two. Like you'd have 2 battery bank system, you'd have one input, one output. But this, or wait, which is the 1, 2, which is bank 2 right here, right? See, yeah, this is bank 2. So you can see the negative. No, yeah,
That's
this is,
three.
yeah, this is,
That's 3.
this is 2. No, this is 2 right here. This is 3.
Okay.
Because look, you can see the pot.
Oh, yeah.
Which one's 3? That one right there?
So this is number 3.
Okay.
So these would represent the the 2 battery bank system.
The imbalance, yeah.
But because we have 24 volts here and 12 volts here, so normally we'd have 2 in parallel here. But I just didn't have more batteries here. But so we've got these 2, but we still continue to charge the 3rd battery bank. And now we've added bank 4 up down here off of the 1 coil. So we have coil number 1 right here, and this is coil number 4 or 3. I think. No. Anyway, whatever. It doesn't really matter which one. Too many wires to try and sort through. We've got the 2 bulbs here. One of them is an LED, and one of them is an automotive bulb. So you'll see that they're not, at 24 volts or 24 watts brightness by any means, but they are still another load.
Those are DC, both of those?
No, this is DC right
And
here,
the other one's
which
AC.
is off of this bridge right back here. And if I disconnect any of them, it will blow out a transistor, which I did this morning.
You don't want to do that.
So I didn't bring any extra transistors, but so we're going to see also the scope shot across the primary positive going into the coil, which is going to be connected to the circuit, and then the other one is going off of this terminal over here, which is the charging positive, but we've got a coil in between it. So, but you'll see the shot. So this the waves. So we're connecting up the trigger, and like I said, when you hear the sound, ding. That you know everything is sound. If I do that and there's a big spark, then we know that there's short. So that's one way, and you can do that if you have a bigger system and you're not sure if you set everything upright. Just use a little thin wire or like a fused link.
Less of a spark or what?
Yeah. So you can see these loads already came on even at the very beginning. And actually they can pulse when I tap that terminal on. So we're going to see here, of course this keeps self-adjusting to the scale. So what I want to do is expand this wave.
There's quite a bit of run out on your rotors there. Does that have any impact at all?
Not much, no.
Okay. I can get an indicator, we can check.
Yeah, I mean, it's not much. It's not bad. So you can see the waves here. This is on either coil number 2 and 3. So what we have here is, 24.4, and this is discharging at the rate that this is charging. 2.5 amps, and this, I can adjust that up or down. So now we're at 2 amps.
Is that just the speed?
Yeah. So of course this is going to discharge less now because we have half an amp less. And I just want to make sure I can see all these in the camera here. Yeah, so there's the amp meter right there. So we've got a charging battery here. This is, hold on, these wires, yeah, okay, so this is battery right here is the battery bank number 4. So that's charging up slowly but surely. This battery bank here is
It's charging. I've seen it go up.
it's going up slowly but surely. And then we have another battery bank here, which is going to also charge up. Oops. It would help if I used the right terminal. So 12.54, and that's going to go up slowly. So we'll put this right here. We'll just let this run for a little bit.
The leads around.
Oops. So now what we want to do is, so you can already see that's 12.55. So what we want to do now is short out some of these coils. Where's that black? I have the black one. Right here.
You can crank up the RPM right now, right, with that rheostat? Or?
Yeah, to some extent. Like, we have to actually put different resistances in there to, but I don't want it to go too fast because we want to look at the scope.
Oh, the waves. Now the bottom waves, is that, what are we seeing down there? What is that?
So
at the other end of the coils, that's opposite polarity.
Oh, okay.
So now what we want to do is short out, if I can, we want to short out these loads right here, or these coils themselves. So right now, we're going to short out coil number 2, I believe, yeah, which has got the AC bulb across it. Again, if I disconnect that, too much energy will flow back into the primary and actually blow one of these out. So we can look at I'll try and stand out of the way here. Okay, so let's look at the RPM. It says 516. Whoa!
Wrong spot.
Yeah, wrong spot, obviously. Or no.
Yeah.
Yeah, well that is too much.
Wow.
Can't do that. Are we sure that this is... Oh, you know what? I crossed the wrong wires. Ouch.
Which ones? Can you put the numbers on there so?
Yeah, I'll do that.
Battery.
Yeah.
Sorry guys, that was a big mistake.
Oh, okay.
Simple little mistake,
What
but
happens?
good
Oh, yeah,
mistake.
good idea.
Here's off.
All right, so
Going
this
from,
totally blew off.
that's,
Look at how much damage that did. Wow, it just melted down the terminal. Well, let's maybe edit that one out.
that's to this battery.
This one?
The one you got, this end here.
Yeah, I know.
That goes to
They
that
should have
one.
gone to that terminal instead of
Yeah.
this one. Whoops.
That's coil 4.
Yeah, exactly. So that's cool.
So this is,
Wow. Yeah, see these wires just crossed the green. I should have had different color wires. So. Anyway, it's obviously discharged that battery a little bit.
Not much.
this is bank 2 here.
So bank 3 was,
That's bank 1. Battery 1.
and this is bank 3 right here.
Okay. And 4 is this one here then.
Yeah, this one is.
I wonder if we could put water in a mole run and then put 2 leads on it and electrocute the moles. I'm trying. I got a mess in my yard right now.
All right. So anyway,
You're
let's
trying-
look at this.
You're trying to collect moles of energy?
Yeah, trying to electrocute them.
523 actually is the RPM right now. We did speed it up, I guess, a bit. Why don't we? See, look, now it's sped up. We got 192. It's
Oh,
speeding
wow.
up.
Yeah.
Now, of course, these charging voltages went down a
I've seen
little
them laugh
bit.
before. That's good.
Okay, so now it's just sped up again, gone up to the RPM, now we're at 2. So this, I just wanted to keep it there. It's not some kind of ideal spot or anything, but you know, these are going to be affected, obviously. Okay, now what we want to do is this right, and not like melt things down. I should have gone right here, because it was this wire.
Oh, you're.
So this wire. Oh! See, that's what we didn't want
Lost
to
your
do.
connection.
It could all blow up.
Now I just did that. Okay, so this is the problem with using these clips like this.
Yeah.
So what happened is now I blew out this another transistor. So okay, this is
Yeah.
what we learned.
Right, that's how you learn.
So what I'm going to do is quickly do this and show.
Where do
What
you get?
happens?
Where do you get the transistors? You get a mail order, right?
Yeah. So what I'm going to do is I'm going to go through each one of these and figure out
What do they cost?
quickly with the ammeter,
$5 a piece.
so you can see it's. And so we just got to figure out which one. One of those. Now, of course, like I said, I've done this several times lately, so it's going to be
I'm wondering how to
one of
test
these
them.
last
That's
two
the way
here.
to test them, to see which ones
Right. Has
shorted out.
Right.
With the amp meter.
Amp meter on each one of the
Yeah.
coil leads.
One of these, which so far,
That's what you need, a 10 ohm resistor in line with that. So you can hook it up and
okay, so it's
get the
this one
meter to
right here at the
stabilize.
front. So what we're going to do is cut off the
Collector. Center lead collector.
we're going to disconnect, well, we've already turned it off, so we're going to just disconnect the wire, and then I'm going to cut off the collector or the emitter.
Yeah, we probably should do the emitter because
And you never know if you've done more damage to
it could be emitter base short. You don't want
yeah,
to
so
lose
you
your
want
trigger.
to disconnect everything.
Right.
So, I mean, we don't need all these, we only need one transistor or two to
Right.
do this. I want to leave the camera on so that we can
Sure.
make sure.
Why would you only need one transistor?
See, now you could hear it click.
Yeah.
So we're back to normal. Of course, some of our things have fallen over here.
Or your meter connections.
But you can see the voltage at least go. This one I have a problem with these. Let's get this all more stable here. So
Because he actually has more than one coil.
Going through
Yeah.
a transistor. Okay, that's what I'm going. So you have
you know, I just need another wire.
So that's really just giving. Use more transistors so it can handle more amperage and.
Let's just
Right.
put this.
Power.
Because
There's another effect too.
Right.
There's,
Let's just put this on here without.
and that is that transistor a MOSFET down there?
No,
No.
just bijunction transistor. BJT.
The transistor again is just a switch, right?
Say
well,
amplifier switch.
yeah,
Amplifier.
Depends on how you operate it.
right.
Right.
But it
So-
can amplify.
Could be a timer. Could
Yeah.
be.
We're operating it non-linearly now
Right.
by pulsing it on and on. If I bias it correctly, I can make that an audio amplifier.
Right.
Not really.
Yeah, and you can stage it.
Okay, so we can see the voltages are kind of. You know, I didn't ever
Yeah.
replace this probe.
See what's interesting about cutting metal, believe it or not. If I could get it. I mean, it's unbelievable that just the
Oh,
things you
yeah.
can do with electronics.
Oh, yeah.
Especially
Oh,
made it a lot more interesting with the
oh yeah. Yeah, it is.
Tesla stuff.
Yeah. It just took a different direction.
Yeah, you can take a device and by how you set it up.
Okay, so we want to look at still. All right. Okay, so what we want to do is short out some of these coils and see this all running. All right, so we're still running here. Okay, good. Wait, that one can't see.
Light. Oh, you got the glare off of it.
Yeah, I got the glare off of all of them. So, except can't see this yet.
Lost the lead.
So battery 4, battery on. We got the amp meters. We got all that. All right, so let's look at this again.
That came on right away.
So that one comes on right away. We can look at this light, how bright it is, whatever. I mean, I'm not talking about
Right.
a ton of energy there, but.
It's there.
So anyway, we can look at the voltages as it starts going and see that they're actually charging and so on forth. So now what we're going to do, get this up to speed, which is pretty much, well, you want to look at the RPM.
As the batteries stabilize out, RPM will come up.
So we're at, you know, about 512, like I said, 511.4, 5. I get this. in the right
If you were to
spot.
take some loads off this, Rick, would that RPM pop up? Is the load keeping slowing it down?
There is no loads on this.
Oh.
There's no mechanical load.
Yeah, but you're putting charging loads on.
Yeah, but now watch what happens when I, this what I'm doing right here
Right.
is going to disconnect
You're gonna
the
do
charging load. You're going to see the motor slow down.
Really?
So this is what the whole point of this part is.
Okay.
Right.
So now we're going to look at, you can listen and watch all of the
Get back.
voltages in that.
Whoa. Brighter.
You get brighter.
It's speeding up.
Well, this is because I disconnected one load.
Yeah.
Yeah.
Which load did you disconnect with there?
Number
The
4.
See, now we're at
4.
508 RPM.
Coil 4.
So that's gone down only a little
Coil
bit.
4.
Coil 4. Okay. Oh, that's nice.
But look at our amperage. We're at 3.5 amps.
Right.
So that jumped up.
So the RPM went slower, the amperage went higher, quite a bit higher. Of course, these batteries charged up a little bit more,
Right.
but we have
Yeah.
greater loss. So let's look at the scope shot again.
Wow.
So you look at the scope shot.
Right.
We came.
So what do you
disoriented, sort of.
What do you?
Yeah,
how
it
can you
increased
explain
the
that in
amplitude,
layman's term?
right.
What just happened?
So what we're doing is, this is running it like without this coil number coil number 4 and its load, which was this charging battery
Where's the coil number 4 over here?
over here, right?
Oh, right here. That's coil.
Now,
1, 2, 3.
now the thing about this is, this didn't totally. This resistance was greater
Right.
than the coil. The coil connection was a firmer connection, and so this didn't totally do what I wanted it to do in that sense. Like, in other words, I would need a better example to show that totally cutting off that coil. But let's try and do this without melting down the next one now.
So what the result was that it slowed down the motor and it was drawing more amps, charging,
Yeah.
charging more.
Yeah, and the two batteries were charging more.
Hold on.
Right.
This is going to
More.
shut itself off.
You
Yeah.
shut off one coil.
Right.
So what do you? Is that a good thing?
Battery 3 and battery 4 was
What?
charging
More.
faster. Yeah.
Yeah.
Oh.
Substantially, actually. Over
Okay,
time.
so now we're going to look at doing the same thing over this one. So this time I'm going to properly follow the wires. And so let's look again. See, we've gone all the way up to
Coil
2.
number 2. Let's just go on to battery 3.
I'm going to slow it down a little bit.
On the battery 3 negative side.
Okay, so we're at,
Is that right?
512 again.
That's the positive terminal.
So again, we're wanting to be at 2
Yeah.
to keep this constant.
Yeah.
Okay, now this time, double checking. See, these wires here I got mixed up when I did that. But anyway,
I gotta get you some masking tape and put little labels on the wall.
okay, so now that load went out.
Speeding
Now this
up.
one's speeding up,
Right.
but let's see.
The amperage didn't change, or did it? It's 2.
Battery 4 is charging faster.
Yeah.
Which might mean we have this one backwards.
Substantially faster.
Couldn't
This
be,
one right here.
Yeah, that was
This is
battery
going
4 is
back
going
and
up.
forth.
Right, but
No,
it's
it
charging.
went up. It
Oh,
went
it's
up.
charging.
It's going up.
It was a 12.59.
Right.
Now it just
It's-
jumped up to 12.62.
Substantially faster over time.
So it may mean that we have this
Back
particular
backwards.
backwards.
The motor sped up. Yeah.
Yeah.
It's
Okay.
fighting.
So
Yeah, it's fighting against the
So
motor.
you have a
we're
coil
fighting. So
reverse.
this. So I've got one coil in reverse.
I was going to talk to you about that.
Because I tested the other ones, which I went back and forth on, and that one I just left it. You're going to talk to me about that. So like, in other words, and then that was, which coil was that number?
Coil 2.
Coil 2 should be,
I'm going to get some tape.
Yeah.
I believe in labels. That way we don't blow up.
A suggestion, Rick,
yeah.
is take the 2 coil wires and put a tie wrap next.
What's that?
Oh,
Put a,
yeah.
put a tie wrap up next to the coil where they come out. So that way you know that's the pair for that coil.
Oh yeah, I mean we're just doing a basic dump
Yeah.
fit. So anyway, this is obviously not
Yeah.
the way we want it.
Yeah.
It would speed up faster, obviously, as it showed.
Right.
But we are still doing this. We're just
Right.
counteracting
Because we're fighting the motor.
Right.
this. So we can show that later on, but I just wanted
If
to
it,
show
if it was phased right, we would have less current draw at the same speed.
yeah.
Right.
We're still having, you know, we're still having the charging results.
Right.
It's still charging. It just
So I think what I'll do is I'll probably do that right now and see the difference. Let's turn this, well, let's turn it off and let the voltages stabilize a little bit so people can see where they'll end up and so forth. I have to look now at the video to see what the voltage was on the primary battery to start with.
it was 24.42. That
To
was it.
start with?
Yeah.
Yep.
That's what we saw on.
24.42 at 9:59 a.m.
That's
Well,
what we
it's
saw.
24.5 right now.
Yeah, right
That's
now.
what we saw
I
on
know.
Steve's. Remember when we were in Steve's
I know.
and we
Yeah.
shut off, went
That's
to
what I'm
dinner,
saying.
come back?
That's why I wrote it down. I wanted
But it's
be
starting
sure.
to come back down. Look, 24. Oh wait, 5.1.
Yeah, 24.42
Yeah.
at 9:59 a.m. And that was.
Okay, that's interesting. Now it's climbing up higher. So there we go.
Yeah.
And then of course over time, if something is receiving a charge, now what's interesting is putting that coil backwards. Well, no, it won't have any influence on the type of energy. The energy will still flow
Right.
either way in either direction. It's just counteracting this.
Water speed and current.
Yeah, because we've reversed the polarity. Of,
Right.
So
Exactly.
that's very interesting. So which one is it? Is it this terminal and this one?
Yep.
For battery
Well, I'm not sure which one.
three.
It's this terminal, whichever coil that goes to.
Yeah.
You have to
All right.
hold
So
on.
Okay.
what I'm going to do, first of all, I've got this disconnect, and we definitely want to disconnect here. So I mean, I'll probably just turn this. Camera off. Okay, so what we actually got, Steve, is show everything. Okay, I've hooked this up. You have to figure out where all these wires go here. This one goes back over here,
D3. Yeah.
and this one, ding, you can hear it. Like so. So actually this battery, the input battery has been charged up
Right.
24/7 from when we actually started. We've got the notes 24/42
Yep.
is where it started, and this is where we're ending up. What's interesting is we only have one battery here. Normally we would have two, but that should not influence it in that sense. So of course that battery is charging up at the rate that this is supposed to be discharging, but we don't have any discharging. This keeps timing out here, so you gotta. So let's see this now. 1.24 amps.
Depending on how good you are.
But I feel
So under load, of course, this is discharging.
Right.
Was that at that voltage under load or under?
That voltage was actually under load. It was
Okay,
under
so
load, wasn't
24.42 was under load.
it? Right. 24.
So maybe it didn't go
Yeah.
in that sense.
Maybe
But
that's what it was.
okay, so
this is under load.
yeah, because I didn't expect that.
Right.
Not until we have this all at the 0 point, which
Right.
I want to show
Right.
in a bit here.
And did your meter shut off over there, Rick?
Oh yeah. All these meters are
Yeah.
shutting off on us when we.
Let me rewrite this.
So let's go over this again.
Who's that motor probably gonna use?
So now at 160.
The electric one. Oh, the rotover? Rotover. You have Texas?
Yeah, see, we haven't reached it. So now we're going back to that 2 amp range. And I'm trying to go a little bit higher because so now we want to do that same thing. Let's see.
Now, which one are you shorting out?
We are going to short out the that coil, that same coil for the
Which one? 4 or?
The AC bulb right at the top, number 3, 2 coil.
2 coil.
So again, look, the RPM at, so we're at over 500, hold on, 550 RPM now, so we've sped up, we've got lower current because the one coil was backwards.
Oh.
Now you can hear some ringing now taking place.
It's trying to speed up, right?
And you can see the scope. We'll have to compare that with what it was before. It's still speeding up, but we're at lower amperage.
Right.
Again, this is the downfall of the trigger circuit. Is it, you know, as charging rates change, charging impedances in the battery, and the discharging will affect the RPM and so forth. But
So you jumped a wire from here to here?
yeah.
Okay. You did it last time and it's a long wire, right? You connected to another coil or something?
Yeah, okay, now I've bumped it up
Okay.
to 2 amps again, so we're at the same point. Now you can hear it speeding up. We'll wait for it to stabilize. 565. So this is actually exactly what I wanted to do. Show it also the coils in the wrong direction, because we're creating a different polarity. So one of these coils was like flipped. So it was fighting.
Right.
In other words, it was a south and a north instead of a north to north and a south to south. So it was creating a drag. So it sounds like we've pretty much stabilized. We're at 2 amps, but we're at 567 RPM. We've got the charging rates, should be all the same. The discharging rate, the bulbs are all the same, but now we have higher RPM because we're actually using this. So these 3 coils again are running for free, free mechanical power, instead of using just an inductor.
Right.
You know, it's like running solid state or a motor. Now we get free more mechanical power. So I'm going to follow these lines very carefully, and now watch what happens to everything. Okay, speeding up again.
No.
What'd you just do?
I shorted out that coil.
That one up there.
So of course we lost the load. Now, we didn't totally, okay, so which was the battery that's charging, which one's that battery? So that one is this battery right here, right? Right here,
Right.
battery 3. So it's still charging because
Right.
we're not totally cutting it off.
Right.
We're actually putting a wire basically in parallel with the coil. So this is becoming a resistance. We probably need a better...
Which current went up.
So this is a generator coil or is it a motor coil right here that you cut off?
It's right now it's functioning as a motor and a generator at the same time.
It has a slight
It's the negative
motoring
resistance.
effect.
It's a negative resistance coil. That's what we could call it.
Right.
So
But it's actually you get better efficiency with it without it, then, right?
yeah. So now what's happening is this wire actually is becoming. So we're at 627. Hold on. $627 RPM. Right?
Yeah, current went up to 2.134.
So now it's slowing down again. Oh, it went up though, right?
Yes.
Current went up?
2.13, yeah.
2.13. Well, that's... So the current drew more as we lessened the resistance. So this is what I showed in the last video. As I added more of my switches on, more loads, the current draw went down until it almost was it was heading towards 0.
Wow.
But that was not on the input side. That was, we were actually measuring the current on the output, which there is no real current there anyway.
Right.
Okay, so let's go back now to doing the same thing with this wire again.
So,
and then
so you're trying to show that you're trying to, in one sentence or a couple sentences, what are you trying to show, Rick?
Right now it's just showing how we're trying to cancel out one of these coils and see the relationship, like to the RPM and to the charging rates and all that.
So you pull out a coil and the RPM goes up and the charging rate goes down.
Well, what we just showed before was with this one. Okay, so this one now is coil number, where's the little bulb? That one's coil number 4.
Coil 4.
Okay, so now this is on the actual positive side. So just to make double sure here, we got this one there. So let's look at this one again. So the current went way up.
Way up.
The RPM's going down.
Yeah. Wow.
So there we have what it takes to run this motor with one coil. We've added the second coil without any circuits on it, which is charging a little load right here, which is warm bulb. So now we've reduced the back EMF even more in the system by doing that, for one. Yeah, somewhat. That's as people would understand it, whether they believe that or not. So let's do that again with the scope.
Right. Can't really see it on the video.
The scope?
Yeah. Oh, there you go.
You got it now?
Yeah.
So it went up in that sense, but it's because the current went way up too. So on the other side was affected. Now there's one more coil. Let's see if we can get that figured out. Which one haven't we done? We haven't done the one across the battery, number 3. So the battery terminal over there is going right here. The white wires. So we've got this down here.
Battery 4 now.
Now I have to make especially sure. Okay, these are the darker wire. So that's over here. Yeah. Okay, so now let's look at this again. The RPM should be around 512, like we had, or no, 562 now.
Okay.
The battery's voltages are changing, so it's going to change speed. And
Yeah, so of course this has gone down here, like I was expecting. So let's look at this, making sure got all the right wires. After you do it once, like I crushed my finger with those magnets now, I'm all nervous with those magnets, but okay, so now we can hear it go down. The amperage in this case, so this is on the negative side of the
Which one coil are you looking at?
number 3.
Number 3.
So now the RPM has gone down to 546. It slowed down. Now we could do this at a higher power level and see, but
Why did it slow down? Because there's more load or less power going?
there's less.
You cut off one battery, right?
Hold on a second.
Okay.
So we got all the voltages. We can see that. We can see the scope. See, the scope kind of cleans up when we remove that.
Maybe we should go up and
Now the problem is that, like I said, this wire right here isn't making a complete short on. It's acting as a resistance.
ideally, you would.
Well, I could actually connect this right up to that
Mm-hmm.
more tightly.
Well, ideally, would you take the coil out of it?
Well, we take it out of the circuit and run it, you know.
Yeah.
But I'm trying to
But you
show
gotta,
continuity
you
here.
gotta short the connection then.
Yeah, I'm trying to show it all like on dynamically, you know.
Yep.
So anyway, we can see all that. So as we add more of these negative resistances, we can not only create more motor power here, but we can create more overall efficiency in the system, and then improve things. So, but now what we were doing with that wire is we were adding actually another resistance across it. So we can show that in a similar way with, for example, this bulb here. Well, I'm going to use this. Actually, I have another bulb that would be more matching. We have to, you know, like I said, match the impedances and all that.
As close as you can.
So this is the same kind of bulb as the other one on there. So let's try and do that with, instead of, well, what we just did across this battery here, the same, or this coil number 3.
Coil 3.
So now we've got, let's see what happens here. So we can see it lights up, but now they're going to be in parallel.
Parallel, right.
Now this goes back to it's doing something similar to that that Minuteman missile, you know, patent, where you can see the resistance on both sides of the
Where are you hooking
transformer.
that up? These two
Right across number 3.
right here.
So we're
Now,
putting,
when you hook it across there, this is still operating too somewhat, right?
yeah. Now
Okay.
let's look at the
Let's see.
voltages
Okay.
on. So it's this
Battery 4.
battery
1263.
4 right here. So 1263. It should go down a little bit. Now it depends on how I hook this up. Just what spot I hook it up to here. I want to try and get. Well, I can't really hook it. I'm gonna have to go. So let's look at the RPMs. RPMs are going down in this one now because it's more of a short.
Current's going down.
Battery 3 went up.
Current's gone down. So now we're at 512 again. So this is almost like.
And battery 3 went up because of, yeah, it's in
Oh,
the,
now the current shot back up.
On this is on battery 4. The current
Yeah,
went
'cause
up,
they're-
or the charging.
yeah.
Oh yeah, the
charging
current
went
went
up.
Went
up.
up.
So this is more of a short.
Yeah, because it was going down. At
So this is a
first.
different impedance that we're putting on this light, right? Whereas the other one's got a battery, which is, you know, a totally different impedance. Well, so we already have this in the same way. If we put a battery across that terminal, it would affect the relationship more. So this is where the impedance matching is very
Critical.
important.
It's critical.
It's critical. It affects everything, not just the frequency.
Right.
Everybody thinks the frequency is the only variable in not everybody. A lot of people think that, oh, just adjust the frequency. Well, no, it's the impedance too.
The
So-
impedance is a load draw, like a light bulb, or it
Well,
could be
it's
a
the-
coil, or it could be a motor,
It's this. It's kind of like you can think about the
Combination.
size,
battery,
the size of the size of the resistance.
resistance. Okay.
So it's kind of like the size, and it's relation to time. So in other words, how fast it can be energized, and how fast it can react
Right.
to the energy, so to speak.
Depends on the component of its inductance, and you're looking at reactance, you know, capacitance,
Like a
and
capacitor.
resistance. Yeah, there's a relationship there, that resonance,
Mhm.
that reduces the overall impedance of those components.
So we should be back now to 600 or 560, 558, which is around the same. It was about 562 before. So now let's possibly wait.
Careful. Which one you taking off?
Yeah, exactly. Let's not do this. Oh, I almost took the wrong one off. Well, but that would have been just the voltmeter.
This is your battery. Now, which battery is that right there?
That's 3.
3, and that's coil 3, right? Is
No.
it coil 3? But no.
No.
It's not connected like that.
Yeah, we didn't quite match the battery.
Oh, that would have been too easy.
Yeah.
I could have just torn
Coil
off.
3 is actually, coil 1 is actually charging battery 3.
Battery 3 is the main battery usually being charged, but because we have these other resistances on it, it's not charging
Very fast.
It's not charging very fast at all.
Oh.
And we're not pushing the
So
motor.
it's connected to 2 and 3 both. Coil 2 and 3, right? Battery 3.
Yeah.
Yeah.
Series.
They're all in. 1, 2, and 3 coils are all interacting with each other.
Right. So you can see though that the relationships
Negative
aren't linear in that sense, where they change with various things that we do quite a bit. In other words, if you were just pushing current on the backside, which you can't account for,
Right.
like you can't account for this amount of power and output at all on the back end, really, because you have the motor. It takes actually more power to run this motor normally. I mean, I've got some big bearings in there, and these are 52 and 52 neomagnets. They put a good bit of drag on the motor by itself. And so, as we saw, if we have if we could actually, we haven't seen it, but if I take out the coils themselves, then this thing will slow down quite a bit. As we saw when we had it reversed, obviously it slowed down. So what I'm trying to say is, as we adjust on the back end here, we will get different results, charging rates, discharging rates, amperage on the front end, and that. So we could go and do one more.
You're running about 23 watts right now. So.
Yeah, so 23 watts run. And what do we want to do over coil number 3? So battery number 4, which is.
This is so complex. I mean, it would be neat if there was a software program.
Well, this is what I'm trying to do.
It takes a lot of study, a lot of testing to come up with those results.
Well,
aren't you using you want to use formulas?
Not really. When you take a couple of different variables. Now the only problem is the proper impedance of the devices that you're using, and that's where it's not so much like the formulas are all basic and all pretty much have been done.
Right.
And it's pretty basic math actually. We don't have to get into the math that reveals, like in this book here. If I'm recording this, I might as well show the book. This kind of math in there is showing at the primary level or the fundamental level what's going on. We don't need to get into that math really. Once because we already know that we're using those processes already. We don't need to prove that or show that to anybody. And people can develop that math. What needs to be done is the application, like you guys.
Right.
That kind of math where we say, okay, this result is happening based upon these impedances, but we're not even at the point. This is not a demonstration to actually look at. When I used my box right here for that little motor, this was more of an approach where I was getting, I was going to show the voltages across the different, well, we can just leave that there. So we're going to look at, now we're on DC. So let's look at this one right here. DC, we've got really, well, it's showing actually 4 volts, which is interesting.
4 volt or millivolts?
Which were you?
Oh no, 4 millivolts, sorry. Yeah, 4 millivolts on that. So let's change it to AC. Now we're going to show something more on here. We've got 2.5, so we're not anywhere close to the 0 point on this.
Right.
So let's look at another one, which is across So we're looking at this one, and what does that read?
2.39.
2.3. So that one is getting closer,
AC.
and that's AC, so let's go to the DC again. And we can look at that with a scope too. But I've shown that in the other video. So now we're at millivolts
Yeah,
again.
9.6.
9.6 AC, or DC millivolts. So let's go over to the last one, which is
Now coil 1 and coil 4, you're going to see a DC voltage on.
which is interesting. Look at the difference in potential. So you have a voltage drop.
That's coil 4.
And that's
135.
135.7.
Yeah, millivolts.
Wait, so this is millivolts, 135 millivolts, so
Right.
13.5,
Yeah.
right?
Right.
And then of course we're going to do the AC.
What coil?
Oh, but this is not the coil that I wanted to do.
No.
We want to look at the other coil. Or wait.
The other one's your run coil on your
Okay, so no,
transistors.
we already did the other coil for this one. Yeah, okay. So that was.
That's going to all the transistors.
Yeah. So anyway, that's my run coil. So you're going to obviously have. What did we show on there? AC wise.
It was 4.29.
4.29 volts.
DC.
No, AC.
AC.
And the DC was 134
Millivolts.
millivolts
Or
times the
point-
2 amps. That's all the
Yeah.
the
Or 0.13.
DC wattage.
So, like I said before, yesterday, on another note,
0.13.
was what this is showing is also in a circuit, not even like this, a pulsing circuit, you can tap into any two nodes or any 2 points that have varying potentials and actually tap into that
On the
potentials
Potential on the negative side of
on the, and then on the negative side, and actually create well, you can create the negative and then benefit from it.
Right.
And that's the difference is on this circuit, like I said yesterday, on the positive side of the circuit, which represents, here the motor, you can't do these kinds of things and get these kinds of gains because it's the negative side that allows the negative resistance, which allows the energy to flow into a resistor or a battery. On the other side of the
So it
circuit,
flows into the negative.
yeah,
It does. Positive to negative.
well, the energy from the environment,
from the environment,
from the
okay,
vacuum
yeah.
or whatever,
Okay.
the energy flows into these batteries here. I mean, the one battery is charging, 1267. That represents the positive energy, in the loop, so to speak, between this battery and these batteries. But these batteries here are part of the energy, and the bulbs are part of the negative side, and actually this trigger. So the energy comes into them, and it can go into the system and be additive back into the positive side as well. So that's where people fail. They look at it, first of all, on the other side. So again, here's this. So they try and do these things on this side as if it's the same on this side.
Right.
And so a positive resistance on here is supposedly dissipating the energy, and you have your losses on this side, and here you have your gains. So what happens here is opposite of what happens here. We have energy coming into these coils that we had extra right here, and this is also a gain here when it doesn't make sense, normally. So, and like I said, these batteries are, in this case, well, this is confusing a bit. the batteries are in series with each other instead of in parallel, so you can see here. So obviously this battery is not charging this battery because of that. But anyway, this is the key, that the energy comes in to the system on the negative side, and if we make it into a resonance and matches our impedances in that, then the energy can be multiplied indefinitely here along this path, and we can have unlimited energy in that sense on both sides of the circuit, or of this negative side here.
And that's without even being resonant, right?
Well, no, we can't add infinitely.
Oh, you have to have
It has to be in resonance for that to be added. Just like when you have in resonance with the regular tank circuit, on the positive side, you can. It's very efficient in that sense. But on this side, it's even more. It's super efficient. In other words, it becomes not just a source of energy like we're showing right here, but it becomes a 0 point process. So you can either put more or less or zero. Okay, what I wanted to do is show the standing voltages, or resting voltages here. This one, of course, is the ammeter, and you can see it's not drawing anything. Of course, the scope is showing. Nothing, no action, of course. So we've stopped it. We can see some of the resting voltages here, and this is climbing back up. So I don't think you must have measured that while it was on load. Yeah. So I mean, it is discharging, obviously. Yeah. But of course, this one was charging. But you can see all the resting voltages. And now, what are you saying, Ken?
On battery 4 is a 12.6 volts. Okay. And we have 2 diodes in series with it in the bridge, which actually means that we're over 14 volts to get that one to charge. And yet when we look at the voltages across coil number 3, we have millivolts.
Yeah. Yeah. So that's the point, is that this is totally different. Now I've shown, or I've done this before, where we've shown the 0 voltage, like an absolute 0, in which and 0 current, 0 volts on that, in which we put, you know, the load in water. So of course there's a bulb, so the terminals can be placed in water. So we're not talking about distilled water. We're talking about, you can put salt water in, and it's not conducting. So it's not.
If you take same water and you put 12 volts to it, it'll start.
Yeah, it will start fizzing. I mean, because there'll be amps and so forth, so to speak. But, so yeah, that's what I'm trying to show with this. On the negative side, it violates these 2 laws, you know, pertaining to voltage and resistance.
Right. Actually, those laws do not apply.
They do not apply. They apply to the front end and the positive resistances, and that's what they're made for. And that's why our meters really are only for positive resistances and not these negative resistances. They can measure where the battery's at and that, but
Where are the 2 diodes you're talking about?
well, it's that bridge, that
bridge.
square, the diamond there.
Yeah.
There's 2 diodes in there.
There's a diode in each. There's 4 diodes.
4 diodes.
4, but you're just using 2, right?
Yeah, it's right here.
Whenever you're trying to charge something, 2 of them are conducting.
Oh, okay.
So you've got inside of here 4 diodes
Yeah.
pointing towards this positive end right here. So this is the negative always.
Oh, okay.
So there's 4 diodes, but we're going across.
Now, if I put a DC voltage on the AC terminals, okay, and I bring that voltage up, I'm going to have to go to 14 volts before I started affecting that 12.6.
Oh, really?
Because there's a diode drop.
So you're saying, is there a
drops.
pulse going in there? There's a pulse, right? And they get a
Well,
pulse?
currently, yes, here.
Yeah.
Here we're getting something, but it's overriding the diode's drop, and then charging the battery.
Yeah, it's a pretty big pulse then.
But when we measure it
It's a
AC
gain.
and DC on that coil, it's millivolts.
Millivolts.
Very, very.
Well, that doesn't make sense then.
Yeah.
Yeah, it doesn't. So it's, we're not, and there's no kind of boost system in this. There's no, we don't have a transformer in this case at all in this. The only transformer is in the primary coil with the trigger wire, and it's 1-to-1. So it's not boosting it at all. And meanwhile, yeah, you can have 12 volt potential is driving the motor, and you can have 300 volt spike on the charging end, but we can see the battery 3 is absorbing, you know,
It is being charged.
and it's being charged. So, you know, and of course, what I want to say also is when these batteries are being charged with the negative energy, like battery 3, right? Battery 4, in that case, can be a positive charge. Battery 3 would be the negative charge because battery 3 is in that path of the negative resistance in that sense. It itself is a negative resistor, whereas battery 4 has been, you know, the coil number 3 has become the negative resistance, in which actually can put out positive energy now into battery number 4. So when you charge with negative with the negative process here, the battery becomes negatively charged, and that can be ideal in now these batteries have been positively charged many times, so I haven't conditioned them in that sense where if I want to run a battery over and over again, discharge it, and it will readily receive that charge a lot easier. It can over time charge a lot faster, and but if it has already been positively charged over time, it will take a while to convert that over, condition it. So, you know, there are two different types of charging, and I'm not trying to show the ideal situation here, it's just some of these different relationships.
But then those negative charged batteries would not be able to be charged from a positive.
Right away,
Unless you
until they
cycle
convert
until
them
you
back.
condition
10
them back.
times or something.
Right.
Well, yeah, it depends on how long you've done it, and so really at the subatomic level, these batteries have been changed, and then it's not like they're ruined, and people think that they're ruined because all of a sudden they'll try and charge it up with a regular battery charger, and it won't charge up because it will be trying to convert it back.
Right.
You know, and I don't have all the, you know, the terminology to explain all that, but
We
but
just
anyway,
come from observation.
the point is you have this process, and that's where to do a true test, you have to do it over time and see these relationships, and understand that.
You guys ready to go to lunch? 12 o'clock.